Okay, well, welcome everyone to the second session on proof systems. The first talk today is about designated verifier snags with one group element, and Jessica will give the talk.
Yes, thank you very much. As already said, this is a talk about designated verifier snags with one group element. I'm Jesko Dimovic, and this is joint work with Gal Anon and Juvalisha. So the question that we are going to consider in this talk is how small can arguments be in the generic group model? And the result we present is they can be one group element plus O of tau bits, where tau is the statistical security parameter. And specifically, this is the first argument in the generic group model, where the proof is just a constant number of group elements. We provide a private coin proof system. This is much smaller than, for example, Killian, which usually you would consider like a hash function-based proof system. But if you have a generic group, you can also use the group as a hash function. So this is also within the model. But there you have omega of tau many group elements. Essentially, for each hash, you need at least one group element. And then compared to this previous work by Butter et al., they also have one group element in the generic group model, but they only achieve 1 over poly soundness. So this is in comparison to our result where we achieve negligible soundness. So if they wanted to also get negligible soundness, then they would have to repeat, amplify a super constant number of times, which would boost to a super constant number of group elements. Okay, but even if we don't care about the generic group model, I think we're pretty good. So the smallest known argument system is a designated verifier version of Sahai Waters, which has just tau bits for again, the statistical security parameter tau. So you have soundness error of 2 to the minus tau. But here the disadvantage clearly is that you're using obfuscation. So this is very inefficient. But so if you want to stick to the efficient solutions that are plausibly implementable, you should, so far you should go with the pairing-based solutions. And here the smallest known proof is 10 lambda bits, where lambda is the computational security parameter. So you think of security against an adversary of running time 2 to the lambda. And so as you can see, our proofs are very competitive here. Okay. So specifically, I'm not only talking about any kind of proof system. Today we're going to talk about designated verifier snags, and I'm going to introduce that model first. So in a designated verifier snag, we have an interaction between a prover and a verifier. We have the verifier. They post a common reference string, or think of it as a public key, and they keep a secret key. And this is independent of any statement. Now, if we have a statement X and some witness W, the prover uses X and W to produce a proof pi, and the verifier accepts because X is in the language. We also want that the witness is much smaller than the proof is much smaller than the witness. We also require that if our prover is lying and X is not in the language, but they send a proof anyway, that the verifier is only convinced with probability 2 to the minus tau. So that's a designated verifier snag. You probably know snags. They are very popular. So this is like a weaker model, but these are still useful in verifying computation. So one of you, for example, if you delegate some AI to some server, the server might want to prove to you that they did the computation correctly. Or the same thing could go for a database. You do a database lookup, and they prove to you that the lookup was done computed correctly. So how do people build designated verifier snags? I'm going to show you the BCIOP template, which basically follows it combines a linearly only encryption with a one query linear PCP, and you get a designated verifier snag. I'll walk you through the components, and then I'll show you how the construction goes. One query linear PCP is an information theoretic proof system where a prover and a verifier interact in the following way. The verifier generates some query vector Q independent of a instance. And then if you have an instance X and a corresponding witness W in some language, then the prover outputs a vector A and a value B. And the verifier receives the inner product between Q and A plus B. And because X is in the language, we want that the verifier accepts. Now we also have a soundness property. So if X is not in the language and these parties interact in the exact same way as on the previous slide, then the verifier should only accept with a probability of 2 to the minus tau. Okay. The other component that we're going to use is a linear only encryption scheme, which first of all, you can think of it as a linearly homomorphic encryption scheme. So you have the standard semantic security notion and linear homomorphism. So linear homomorphism is if you have a ciphertext encrypting D and a ciphertext encrypting E, if you can combine them in such a way that the ciphertext that this is decrypts to D plus E. But you have an extra property where if you have a bunch of ciphertext and you give those to an adversary and they output a ciphertext at the end, one of two things happens. Either decryption will fail on this output ciphertext, or you will be able to extract a vector A and a value B such that the output of the decryption of the ciphertext is exactly the inner product between Q, A, and A plus B. So in a way, the adversary can only compute linear functions on the values in the ciphertext. That's why it's called linear. Okay, and now I'm going to go into how to combine these two notions to get a designated verifier snag. The verifier generates a linear PCP query Q and encrypts each of the elements of Q and puts the ciphertext into the CIS. The prover generates a vector A and a value B and evaluates the function that of the inner product of A and Q plus B, but homomorphically on the ciphertext. So now pi is just a ciphertext encrypting the inner product between A and Q plus B. And the verifier can decrypt this proof pi because it's just a ciphertext, and then run the linear PCP verifier to verify. Now we have that the size of pi is just the size of one ciphertext in this linearly homomorphic encryption scheme. So clearly, if we want to minimize the proof size in this kind of template, we should pick the smallest linearly homomorphic encryption scheme that we know and try to instantiate this template. And that's what we're going to follow. This is the recipe we're going to follow. The smallest known to me publicly linearly homomorphic encryption scheme is packed al-Gamal, and I'll quickly walk you through that. So it encrypts a vector M of n small numbers, and its public key is just some random group elements, and the secret key is the corresponding discrete logarithms of these. So the arrow is a vector. So a ciphertext is for some random r, g to the r, and then public key raised to the power of r times g to the m. So we have the message in the exponent. And again, everything that has an arrow is a vector operation. So this happens component-wise. And this is linearly homomorphic because if you have two ciphertexts, one encrypting m, the other encrypting m prime, you can multiply each component and you will get a ciphertext encrypting m plus m prime. And you can simply decrypt by taking this g to the r and raising it to the ith component of the secret key, and then dividing the ith component of the ciphertext by it. And then you will have g to the m I, and you run the discrete logarithm on this to obtain mi. And clearly, for this to be efficient, you need that the values of m is small. That's why I said it encrypts small numbers. Okay, now this is a ciphertext with n+1 group elements, so this is not very small yet. But luckily, there is a technique developed in this traptor hashing paper that allows you to compress this ciphertext after you've done some linearly homomorphic encryption on it. You can compress it and make it smaller. And I'll quickly show you the technique how to do this. For this, you need a distributed discrete logarithm. This is a technique developed in function secret sharing. Here you have there's a protocol between two parties, Alice and Bob. And Bob has a group element g to the a, and Alice has a group element g to the a plus b. And imagine b is a very small, like a binary. Then binary or small. And then they get Bob derives the value c, and Alice derives the value c minus b with like some 1/poly probability, but they don't interact at all in this protocol. So this is everything happens non-interactively. Okay, so now we have this property that we kind of converted a sharing in the exponent of something to a sharing of exponent in the sharing of a value of the same value additively. And how are we going to use this in a packed Gamal? So we take our ciphertext and we keep the g to the r element, and we compress everything else using this distributed discrete logarithm and modding it. So we know that each component of our vector m is small, and let's say that the small means smaller than some value p that is like predefined. So we keep g to the r, and then the second component is just a vector of values mod p, because we've reduced it to an integer using distributed discrete logarithm. And then you can decrypt in the following way. You take a g to the r, you raise it to the power of the ith secret key component, and you subtract the ith value of these mod p values. And because g to the r to the power of ski is the same as the ith public key component raised to the power of r, the correctness of the distributed discrete log works, and we get we get correctness with some 1/poly probability. Okay, now we have a ciphertext of size 1 group element plus n times log p of n plus n times log of p bits. And the question is now, okay, this is clearly a linearly homomorphic encryption scheme, but is it linear only? And to us, surprising answer is no. Actually, we were going into the project expecting it to be yes, so I was very surprised. So, and the problem really is the decryption failure of the distributed discrete logarithm. Sadly, I don't have the time to go into this, but please talk to me about it if you're interested. But there's one property that we can prove about this encryption scheme in the generic group model, namely that it is isolated homomorphic with a new name. So we still have semantic security and linear homomorphism, but we also have that if we give an adversary an encryption of a matrix in row-wise encrypted, then one of two things happens. Either the decryption fails, or it is a function of the matrix. It is the n outputs of n functions, but the functions are applied column-wise, so the columns cannot interact. Okay, and we prove this in the generic group model. Okay, so we have the BCIOP recipe, but we have made the linear-only encryption weaker, so now we need to make the proof system stronger to match this, to still get a designated verifier snark. And this is exactly a strong linear MIP, which again is an information theoretic proof system. Here the verifier has a matrix, and the honest prover has again a vector A and a vector B now, because we are talking about encryptions of vectors. And the verifier receives A times Q plus B. And they should accept if X is in the language. In the case that X is not in the language, the provers send different functions, and they are applied column-wise. And the proof is the function applied to the columns. And the verifier should only accept with probability 2 to the minus tau. And so now we combine these notions. The construction looks pretty much the same. And correctness also kind of looks the same. But now we have completeness as long as the decryption doesn't fail, but we can compensate for that. And we have succinctness because our ciphertext doesn't really depend on the size of the witness. But we only get like plausible practical snarks because both prover and verifier are like linear in the size of the witness. But how does soundness work? If X is not in the language and the prover sends a proof pi, we can extract these functions f1 to fn, and then this reduces to the linear MIP soundness. Okay, here's some open problems that we also illustrate further in the paper. First, we think that with some like extra work, we can get the proof system to be smaller, just one group element plus approximately tau bits. The second one is to make the entire thing reusably sound. So this was like a one-shot soundness. And the second, another thing is to improve the prover and verifier complexity, the verifier complexity to like fourth root of the witness size. We in the paper we have like a specific steps that need to happen for this to work that I think are very realistic. And the fourth and final one is find some way to use this strange homomorphism of this compressed El-Gamal version in a productive way, not just ruining this construction. Okay, so here the takeaways. There are very small group-based designated verifier snags. This is the recipe to build them, and compressed El-Gamal is not linearly homomorphic. Thank you.
Are there any questions? Do you know if there are any lower bounds for designated verified snags about, I mean, the size? I know in Grot 16, they have some lower bounds in the public coin setting.
Yes, so the lower bound is essentially just you need for tau bits of soundness, you need tau bits of proof.
I see.
And that is matched by a designated verifier version of the high waters.
I see.
So
it's just not efficient.
yeah, it's I/O. Yeah, but I don't know of any lower bound in a like some generic model that rules out I/O or something.
Thank you. Are there any other questions?
I'm saying zero group elements is impossible since it matches that.
Okay, let's thank Jesco.
Yes, let me switch out.
Okay. Luigi Russo will give the second talk on universally composable snarks with transparent setup without programmable random order.
Thank you for the introduction. This is a joint work with Christian and a bunch of Italians, Matteo, Michele, and Luisa. So despite the issues that Canetti himself was pointing out a couple of days ago, the universal composability framework is the gold standard to analyze the security of modular protocols, in particular when dealing with concurrent executions of multiple subprotocols. Well, in the UC, these modules should not just expose an interface to the clients interacting with them, but they should also capture some behavior in terms of ideal requirements. And this is why, rather than calling them modules, we just call them ideal functionalities. And so designing a complex protocol in the UC framework basically reduces to designing a nice orchestration between different ideal functionalities. One of the main results of the UC framework is the so-called composition theorem that states that a protocol that UC emulates an ideal functionality can safely replace the functionality in our larger protocol. And we can apply this theorem over and over, and essentially what we get is a concrete protocol that is as secure as the one that we have designed. Now, we can come up with crazy ideal functionalities, but there is already a variety of them, standard, well-known functionalities, ranging from very simple ones, for example, the commitment schemes, to complex ones, for example, for ideal ledgers or voting. And the focus of this work is about the non-interactive zero-knowledge proofs, or NIZICs, with a particular emphasis on the succinct ones, namely ZK snarks. Well, because they have tons of applications and they're used in larger protocols that are deployed in real-world applications. ZK snark formally is a protocol that allows a party, the prover, to convince another party, the verifier, that given a public input X and a public relation R, it knows some private input W that we call the witness, such that X and W is in the relation R. And ZK snark has some nice features, namely zero knowledge. So at the end of the protocol, roughly speaking, the verifier learns nothing more than the fact that X and W is in the relation R. The proof is succinct, so it is at most sublinear in the size of the witness. The proof does not require any form of interaction, so the prover can generate this proof on its own and later give this to the verifier. And finally, ZK snark is an argument of knowledge, so it satisfies a property called knowledge soundness, meaning that if the verifier accepts, then with overwhelming probability, the prover must know some valid witness W. And if this property holds even in presence of simulated proofs, we say that the ZK snark is simulation extractable. Now, being non-interactive and zero knowledge, the ZK snarks require a formal setup. So the prover and the verifier need to agree upon a common reference string, or CRS, and this can be generated, for example, by a trusted party. So we say that the setup in this case is trusted, but the problem is that in practice, trusted parties do not exist. So we need to replace this trusted setup with some complex MPC protocol or ceremony, and in practice, things can go very bad. For example, even when deploying the Zcash protocol, there was some vulnerability that had to be fixed later on. So rather than relying on a trusted setup, it's better to rely on transparent setup. Namely, there is no trusted party involved, there is no trapdoor, no toxic waste that is generated. And one of the most accepted forms of transparent setup is the random oracle model. Namely, the parameters are just generated by invoking this uniformly random function that is available to both the prover and the verifier. But notice that in the most generic case, this random oracle is used as a local resource. Namely, this function should be sampled by the prover and the verifier just before their execution. And this means when we move to the UC framework, that if we consider, for example, two concurrent executions or two sessions of an ideal functionalities, such as a snark, that uses a random oracle as a local resource, then these two random oracles should be independent one of each other. But this does not match what happens in practice, where people just instantiate the random oracle with an hash function, and most of the time this is the same hash function. So a better approach would be to model the random oracle as a global resource that in the UC framework means to model it as yet another UC functionality. And here the parties or the functionalities can interact with the global random oracle just by querying it and observing its output. And notice that this matches better what happens in practice, because now there is only one global random oracle. We can instantiate it once, for example, with an hash function. But when looking at the UC security, the works that prove the UC security of proofs of NISIX, there are a variety of them, but only a few of them focus on succinct proofs and ZK snarks. In particular, these few works either need to rely on a trusted setup, or they need to require some form of programmability of the global random oracle functionality. And the main question behind our work is whether we can obtain UC secure ZK snarks that have a transparent setup in the global random oracle model without any form of programmability. And we show that this is possible. And we propose two lifting compilers. In particular, the first one is an intermediate compiler that lifts simulation extractable snarks to their straight line counterpart. Here, the straight line means just that the extractor is not allowed to do any rewinding. And this compiler preserves not only the succinctness, but also the transparency of the setup. And then we show yet another compiler that lifts straight line simulation extractable arguments into UC secure ZK snarks in the global random oracle model without any programmability. And again, this compiler preserves succinctness and setup transparency. So giving you a wider picture, we can, of course, chain these two compilers, or we can just apply the second one, let's say the UC compiler, if our construction already achieves some form of straight line simulation extractability. For example, this is what happens with the Mikali proofs or the BCS-based, IOP-based constructions. Let me focus now on the second compiler, this UC lifting compiler. And to show you how we achieve UC security of a ZK snark, I first need to introduce you what means for how we capture the UC security of a ZK snark. In particular, we need to write down the ideal functionality of a ZK snark. It has a proven interface and a verified interface. Here, for simplicity and for time constraints, I just focus on the prover. The parties, in particular the prover party, can query this functionality on input a pair x and w. If this x and w is in the relation, then the functionality computes the proof. This proof is generated by the UC simulator on input just the statement. And this intuitively captures the notion of zero knowledge. But notice that this is simulator. In what we would like to have is a simulator that is able to simulate this proof, to compute this proof, without using any trapdoor and without programming this global random oracle ideal functionality. And if this looks like an impossible task, that's because it is. This simulator would be an adversary to the knowledge soundness of the protocol. However, this impossibility result holds. Does not hold if we allow the simulator to run in the super polynomial time or the SPS model introduced by PASS. So how do we circumvent this impossibility? So we rely essentially on an OR trick. So the prover needs to prove that either he knows a valid witness for the statement X or he knows a solution to a puzzle. For some reasons, this puzzle is generated by querying the global random oracle. You can think of this, for example, like solving the discrete log of a group or of a random group element. And then we need to modify the UC functionality here, because now the proving interface does not use the UC simulator to come up with the proof, but invokes an adjoined oracle that can run in super polynomial time, can brute force the puzzle, finding the solution, and then this solution is used to generate the proof. Now, you may wonder what happens now in the UC framework, since we are introducing an oracle that is running in super polynomial time. Now, the adversary in principle, the UC adversary, so the environment, may abuse of this extra power. But notice that this oracle cannot be directly accessed by the parties, but because it is shielded from the functionality. Namely, the prover, only the prover that provides a valid pair in the relation can actually see the output coming from this oracle. Here, this slight modification of the UC framework leads to a well-known framework named UC with shielded oracles. And here, the main point is that the simulator, our simulator, UC simulator, should come up with a proof by essentially simulating this, by essentially brute forcing by simulating the oracle, and so by brute forcing the puzzle. Notice that proving security in this UC variant means to have implies to have security in the SPS model, and that's fine for our impossibility result. Since there is a bit more time, let me go over the first compiler. So this is the compiler that leaves straight line the simulation extractable snarks to their straight line counterpart. And this compiler is not entirely new. We base our result on a UC compiler of Ganesh et al. But with some concrete differences. In particular, let me first recall what this JQ compiler does. Roughly, it applies the Fishlin transform on top of random point evaluation of a polynomial encoding of the witness. Namely, the prover encodes the witness W with some function, with some polynomial f, commits using a polynomial commitment to f, and then provides two proofs to the verifier. The first one is a proof that he has the valid witness W associated with the statement, and he proves that the commitment to the encoding of the witness has been done correctly. And as a second proof, he provides an evaluation proof of this polynomial f on a point z that is obtained as a challenge by the verifier. And now, from this second proof, we require some predicate. In particular, when we hash this proof, we should have, for example, a certain number of zeros as a prefix. And this is essentially a proof of work. And this is where we can apply the Fishlin transform, because the extractor now can observe a bunch of these proofs and can run an interpolation can interpolate the polynomial f, from which it can decode the witness. But notice that this approach works as long as the NISIC for the second proof has two properties, unique proofs, and some weak form of zero knowledge that is called evaluation hiding. This is to prevent leakage of the polynomial f, because otherwise the verifier could reconstruct the witness, or at least could have some information about, some leakage about the witness. And these two properties, uniqueness of the proofs and weak form of zero knowledge, they don't really match one of each other, but their compiler, this GQ compiler, works because they have a trusted setup. They use the KZG polynomial commitment, and the magic of a KZG polynomial commitment allows to have unique proofs with this weak form of zero knowledge. But we cannot rely on that because we want to have transparent setup. And I just give you an intuition of how we can bypass how we can solve this issue. We use a randomized encoding of the witness. The witness should be encoding in a randomized way, and this is to prevent leakage of the witness. So this gives us some evaluation hiding, And to do that, we use some secret sharing, additive secret sharing, and some PKE. And then once we have this randomized encoding of the witness, we can run a deterministic inner product argument a la bullet proofs on top of some Pedersen commitment of the witness. Notice that here we cannot use zero knowledge inner product arguments because otherwise we would not have unique proofs. And this is where most of the technical part, I would say, the technical challenges were arising. Thank you for the thank you. If you have any questions, I'm happy to take them.
Any questions? Do we have any UC secure ZK snarks either in the transparent or in the trusted setup setting that are concretely efficient or like plausibly concretely efficient?
Yeah. Depends on what you mean by UC security and under which assumptions. We have, for example, growth 16 that has been recently proved to be UC secure, but with some GGM involved.
Yeah.
And you have these these PCP-based constructions, these PCS constructions. They also have some UC security in the global random oracle model, but they require the random oracle to be partially programmable.
I see.
So it's so we do have them.
I see. Do we also have like some global version of like these other idealized models like GGM and AGM?
Sorry?
Do we also have like some sort of a global variant of like the global random oracle, like a global variant of these other idealized models like GGM or AGM, or does that not make sense?
I think they in this work on the UC security of growth 16,
yeah,
they need to basically come up with they need to solve this inconsistency, or at least they need to solve the issues when combining the UC security and this GGM involved.
I see.
So if this answers.
Thank you. We have a lot of time for more questions. Okay. Let's thank Luigi again.
Sure. Oh, yeah. Sorry. Yeah, that'd be great. I don't care about using that presenter view. I don't need it. Just same way as against is fine. Yeah. Good to go forward back.
Okay, so our next talk is by Brent on a pure indistinguishability obfuscation approach to adaptively sound snarks.
All right, thank you. So yeah, I'll be talking about a pure indistinguishability obfuscation approach to adaptively sound snarks. This is joint work with David Wu. And hold on a second. Oh, there they go. Okay, so succinct arguments or snarks for MP are a really fascinating object. Here we have a prover which has a statement X and wants to convince the verifier that it's true or in the language using its witness W. And both of them are given a common reference string generated from some trusted setup process. So what the prover, wrong way, now I got it. So what the prover will do is use the proof algorithm to generate a proof or certificate that it sends over in one shot to the verifier. And the verifier can check this using its verify algorithm without any further interaction, right? And intuitively, we want to have two properties of this. First of all, it should be sound. If X is not in the language, it should be hard for any computationally bounded prover to convince the verifier otherwise. And second, we want things to be short or succinct. That is, the proof size should be polynomial in just the security parameter and independent of the statement length or the witness length. And if we try to think how do we get snarks, I can break it into, one way to break it is into two categories. The first one is if you use something like a random oracle heuristic, knowledge assumption, generic groups, that type of thing. That was pioneered by Killian McCallie. And I should say there's been many, many, many works along this line. I think we just kind of saw two in this category right before me. But we might also ask, okay, what if we're going to be take the stance that we want to have standard assumptions? So no generic groups, no knowledge assumptions, stuff like that. What can we do in this case? This tends to be a path I would say much less traveled by. And I think the main work that the main work from a while ago that I can point to that did this was this work by Amit Sahai myself, which showed how we could get non-adaptively secure snargs from indistinguishability obfuscation that came out in 2014. And if we combine this with this Jane, Lin, and Sahai work, showing how they could get obfuscation, indistinguishability obfuscation from well-founded assumptions, that actually does give us a solution from what you might argue is close to standard assumptions. The limitation, though, of this work is, of course, in the title I have here, which is that I say it's non-adaptive. That means in the security game, the attacker has to declare its statement X before seeing or independently of the common reference string. Now, in real life, of course, attacker will see the common string first, and you can imagine different systems where building upon this where maybe that will lead to an actual attack. So you can think of it as the right definition should be adaptive security. Okay, so for getting adaptive security, this was actually perhaps surprisingly open for about 10 years or so. And then last year, two works, one with myself and David Wu, and another one with myself and Mark Zandri, showed how we could get adaptive security from indistinguishable obfuscation, but if we use some additional number theory, discrete log, factoring, or learning with errors are some of the things we could instantiate it with. So it requires additional number theory. What I want to do in this talk, and we will do, is to get what I call a pure indistinguishability obfuscation approach. Trying to coin this term or make it happen, but we'll see if it works. But here I mean by just indistinguishability obfuscation and one-way functions. All right. So to understand our techniques, let's first take a look at that construction from 10 years ago, kind of get a sense of how it works, and then we'll see how this construction builds upon it and how it's different than it at the same time. Okay, so good news is only two tools for building this. The first one is indistinguishability obfuscation. This is when I take a program or a circuit, a function, and I run it through an obfuscator, and it outputs another program which behaves the same way in the first one in the sense that for every single output, every single input, the outputs will agree, but it will be perhaps a bigger program. And I also want it to be functionally, indistinguishable. So for example, if I take any two programs which are functionally equivalent, and I flip a coin, I'm going to obfuscate one of them. As an attacker, you won't have more than negligible advantage in distinguishing between them. Okay? So that's indistinguishable obfuscation. The second one is something called punctual PRFs. So a punctuable pseudorandom function is like a pseudorandom function. It's a keyed function, has an input, gives you an output, except for the idea is that I can take this original master key or PRF key, and I can kind of cripple it or puncture it at one point, which means that it will work everywhere except for X star. So let's see here, if I do a key gen, I say what I want my security parameters lambda, I say what I want my input length to be, what I want my output length to be, and it'll give me a master key. I can also puncture this at any point X star of what I choose. And then also there's an evaluation, just PRF evaluation algorithm which will work on a punctured key or a master key, right? And two properties of one is punctured correctness. Everywhere except for X star, this punctured key and the master key will agree with each other. And the second one is that we have security at the punctured point, even if you have the punctuable PRF. Okay, so in particular, the punctuable PRF, you cannot distinguish the function's evaluation versus a random string. Okay. Okay, so let's take a look at the 2014 scenario. Good news is we can fit it kind of easily in one slide. The first step we're going to do is to run a setup. For setup, we're going to run the keygen algorithm for the punctuable PRF. The input length is going to be statement length, and the output's going to be security parameter. We get a key K for that. The next, we're going to consider two programs. The first one I'm going to call gen proof. This will take as input the statement X and a witness W. And if it doesn't agree according to the relation, this program just quits. However, it does agree it outputs the punctuable pseudorandom function, and I'll kind of call that a signature, in my words, I'll call it a signature on the statement X. All right? The second program is going to be a verify program. It will take as input the statement X and a proof pi. It will also just essentially evaluate the PRF and compare the proof pi to the other one in order to decide whether to accept. It actually runs as one-way function, lowercase f on both sides, but we can kind of ignore that. Yeah? And we can't give out these programs in the clear, otherwise it's not secure. So we simply just obfuscate both of those, right? And we get an obfuscate proof program, obfuscate verify program. That's the common reference string. And then the prove and the verify is pretty simple. To prove, I just run the program that proves, and to verify, I run the program that verifies. And that's it. So really what I do is I kind of, it's in some ways a lot different than these other proof systems you'll be seeing, in that I just say, hey, proof program, I'm going to demonstrate to you that it's okay, give me a signature, and the verify program just verifies the signature. And that's pretty much it. Now, I won't go into the proof of this earlier scheme, but I will say it's selectively secure. And if you look at its proof, it uses the selective security in a pretty fundamental way. Like when you tell it X star, it goes to the statement X star and the reduction sets things up to only really work that way, okay? So if we want to move to adaptive security, the first thing that would pop into my mind is, oh, there's usually a cheat for this. If we have sub-exponential hardness, what we can usually do is go from selective to adaptive via guessing, okay? And let me talk about how that works. So polynomial time hardness says all polynomial time attackers have negligible advantage. And sub-exponential hardness will say for some constant between 0 and 1, polynomial time attackers will have advantage 2 to the negative lambda to the c times negligible, okay? And what can we do with this? It's what I call an inflating step. So I'm going to take my old security parameter and let's say the statement length, add them together and raise it to the 1 over c, which will be some number. And I'm going to get a new, bigger security parameter. And now if I run my system, which was selectively secure on this new security parameter, my hardness is now 2 to the negative n times negligible, right? So what I can do is I can do things like take a 1 over 2 to the n loss in my security reduction. If I need to do hybrids, which are exponential, like in n, like 2 to the n hybrids, I can do stuff like this. Okay, so that's what it gives me. It kind of gives me security for free in some sense. And we've seen it in other primitives so far, where we kind of got an adaptive security in a generic way like this. Yeah. Okay, so the question is, does it work for snargs? Answer is yes and no. It does work. It does give you security, but things get bigger exactly due to this inflation step, and they will get bigger and grow with n. The common reference string will get bigger because that was that depended on the security parameter. That's kind of okay at least by the rules of snargs that I presented. But the proof size will also grow in n, right? And this is no longer a succinct proof, according to what I called succinct. Yeah. Okay, so we need to figure out something else. To get adaptive security, surprisingly, yeah, it did remain open for a while. And to do this, what we're actually going to do is we will do this inflation step, but I'm going to do it in a more careful way before, where I just kind of did everything the same way. In particular, my obfuscation and my punctuable PRF, I'm going to inflate exactly as I told you. And that means it will cause the common reference string to grow with n. But for my one-way function, that kind of signature object that came outside, this won't be inflated. This will stay pretty much as the security parameter. And the rules of the game now, if I inflate like this, if I have a proof only involving, let's say a reduction step only involving obfuscation and punctuable PRFs, I could do 2 to the n of these, and it would be okay. But if it's something like involving the external one-way function, I better not have it in one of those 2 to the n steps. Okay? Okay, so for the construction, it's going to look a lot like before. Here we will have a keygen algorithm, but instead of outputting one punctuable PRF, it will output a pair of 2 of them. So either one of these 2 could be used almost in the same way to give a proof or verify proof. And there's going to be one more PRF, which will be called a selection, I call it my selection key, which will select which one to use. So my proof program, same as before, take an input X, witness W, quit if the relation doesn't match out. Otherwise, the selection PRF is going to tell me which of the two keys to use, and I will use it as before. And now I get a proof, which is the bit B and Z. Okay. Verify program has both keys. I will give it the proof, which will tell you which selection bit I used, and it will just compare Z to the PRF evaluated on the key K of B. Okay. So pretty similar to before, but now we just have these two different options. And to prove security, it's actually pretty simple. We can break it into two parts. The first part is we're going to establish something. I'm going to say that if the attacker wins at all, let's say it wins with non-negligible probability epsilon, with about epsilon over 2, about half, it's going to win what I call off path. That is, the proof or the forgery it produces will have a bit be opposite my selection bit. Okay, so I'm going to just establish this fact. Intuitively, it comes to the fact that, well, the attacker's advantage altogether has to be concentrated on false statements. Can't win if it proves a true statement true. And the selection bit is actually hidden via obfuscation and the punctual PRFs in here. And also, since those are just in the common reference string, I get this 2 to the negative n type security property there. So yeah, intuitively, it's hidden. I will say that this part of the proof is almost is module syntax really just borrowed from the previous works. So I won't go into actually showing this, but yeah, so this comes to the prior works. And now what I want to do is find a different way to embed the challenge. So now I don't even care whether the statement's true or not. I just know the attacker is going to do one of these, what I call off-path forgeries. Okay, whether it's on true statement or false one, I won't even care. But what I want is when the attacker does it, it will help me solve this, find a preimage to this one-way function, no matter where in the heck it was, right? I won't know ahead of time where it was. And before we used number theory to do this, like a re-randomizable one-way function. Okay, so here's how I'm going to do it. I want to do I want to say, well, the attacker is winning, off-path winning, coming into this game. And I'm going to argue that its advantage is almost the same when I change to a different setup, to a different hybrid. So let me describe to you what this is, and then kind of sketch out how we get there. So in this new hybrid, I'm going to set we're just going to first choose y star is equal to f of r, whereas lowercase f is an injective one-way function. And I'll circle back to the whole injective part in a little bit. Okay, so before the verify proof program was an obfuscated version of something that looked like this. Now what I'm going to do is say if it's on path, it will just do the same, right? We'll just behave the same way as before. But now if it is off path, it's going to do something different. It's going to compute like this. It's going to take that proof part z, XOR it with the punctuable PRF evaluated at x, and run the one-way function on it and compare to y star. And only if this equation holds true will it actually accept. Okay? So I changed it from, let me go back, changed it from this to something where it verifies differently off path. And what I need to do is do a hybrid or a sequence of 2 to the n hybrids to change this for every single statement. Okay? Oh, and it's also important by the time we get to the end of here, the gen proof program should be unchanged. It might kind of change in the middle, but it won't know R, and that's going to be important. Okay, so let's see how we just change a single statement. Originally, we have that it's doing this check. First thing I can do in a sequence of 2 steps or so using obfuscation and punctuable PRFs is I can hardwire in a value t, just random value t, and check that it's equal to that. That's just kind of hardwiring in the punctuable PRF function, right? Next thing I can do is change the checking to z XOR some random t prime and see if that's equal to the randomness r, right? And this will come from just obfuscation and t prime XOR r is distributed the same as t. Then the next step I'm going to do is a little more tricky. I'm going to take an injective one-way function on both sides of the comparison and put it there. And the fact that this comes from obfuscation and the fact that the function's injective. If this weren't an injective function, what I'm saying is false. Okay, but this check is actually equivalent. And then finally, I'm going to take the punctual PRF in the opposite direction, and I'll just be doing this check at the end, which is where I want. Okay, so in the proof, we do this over and over and over again, 2 to the n times. But notice the proof steps, I only mention punctual PRFs. I only mention obfuscation. I don't talk about the one-way function. Okay, so by the time we get to the end, we have something that looks like this. And the good news is it's pretty easy at this point to do a reduction. Let's say the adversary does any one of these off-path forgeries and get you a Z where this holds. Well, you can just XOR out from Z this PRF, and it gives you a solution to the injective one-way function. Yeah, and so kind of this is the idea. We're going to put, in some sense, the same one-way function challenge everywhere, and not use number theory to do it. Oh, okay, so kind of tying off a few things. I did promise you from one-way functions to be, ultra pure, let's say, as opposed to injective one-way functions. There's two answers to this. One is that prior work does give you injective one-way functions from one-way functions, so that's a pretty easy answer. We actually didn't use that path. Our method, we wanted to do something a little different. We showed how we could do it with injective one-way functions, but we're actually sampling the one-way function, or something close to it, was inefficient, took exponential time. Now you might think, oh, that can't be good, that kind of stinks, right? But the important point here is that the one-way function is not used in the construction. It only appears in your proof of security, right? So what you can actually do is if you're doing a non-uniform, if you're proving security with like a non-uniform reduction where you're given a vice, the inefficient sampling can come as the advice. Okay, so it's actually, this is good there. And okay, maybe it didn't matter so much for this result, but I think it could maybe help, maybe in future work. There are a couple other things like homomorphic encryption or garbled circuits where you could have a primitive that you don't use in the construction at all, but you actually do use in the proof of security. You could like just kind of pop up in some hybrid when you're going through things. And there, it might be, there you don't have obfuscation, and maybe you want an injective one-way function. So it'd be interesting to see whether this comes up again or not. Okay, so yeah, and just to conclude, I want to mention, I talked about the second category. There's been other works, neighboring, not quite doing different things, but I think worth kind of mentioning. For example, we can do snargs from learning with errors if there's propositional proofs. That was neat. There was another work that observed that I think even someone mentioned it a couple talks earlier, that the SW14 work was actually already adaptively secure, but if you're okay with designated verifiers, we have adaptive batching of snargs, and even using these propositional proofs, you can get universal snargs. And I'm sure there's several other works. It's a very active area, and probably a lot I didn't get the chance to hit on to. Okay, so thank you for your attention.
Any questions? What was your motivation of like doing your own one-way function, as opposed to
Okay. So one answer is that we found it interesting to do it that one way. Another way is we didn't know about the prior work until we already did it. And I'm going to stick with the former answer, but I'm just telling you there's another possibility. Yeah.
So it looks like that you be in a situation where when you do sampling, trying to get the injective of a function, you need to be indistinguishable, right? The case where it's injective from the case where it's not injective, right? To make the proof to go through.
So the way I'm thinking of, by the way, just to finish off on Yale's question, I do think it was interesting still to see two different ways, but yeah, I think you know why now. So no, we don't. I think the way to think of the way I presented it here, it is just an injective one-way function. Yeah. So initially, we're not using. You talk about the proof where I brought in. Okay. So hold on. I don't know if I can get to. Tell me if it's going a little slower than. Okay. So you're talking about this like hybrid 3 step or no?
The article you were on injecting as of the one.
Yeah, it's from going from hybrid 2 to hybrid 3, right? So in hybrid 2, you can see like that there's only one value on the left-hand side, which will make this equality work, right? Now, if I happened, I don't know, let's say I happen to have a non-injective one-way function where there'd be some collision, and maybe once you know one, it's easy to find its sister or something like that. then you could very easily test whether I'm going to hybrid 2 versus 3. So if it were not injective, and in particular if we're not injective in a, yeah, it could be possible, like maybe it's not injective, but it's hard to find it. Maybe you could, yeah. So yeah, it's possible there's something, a little relaxed version of injective that might also work, if that's, oh, that's your question. Yeah. Okay, thank you.
Okay, let's thank Brent again.
Bring that up. That's forward, that's forward, that's backwards.
Huh?
Yeah, and that's what I was.
Oh, I'm already mic'd up. I see. Let me try.
Okay, so Surya will give the last talk on incrementally verifiable computation for NP from standard assumptions.
Hi, everyone. I'm Surya. Yeah, today I'll be talking about IVC for NP from standard assumptions. And this is based on joint work with Pratish, Abhishek, Tanjong, Alexis, and Amit. And I will be very upfront right now that I'm including IO in this box of standard assumptions. At least one of my co-authors believes this, so I think that's a valid title for my paper. Okay. So what is IVC? So this was like I wanted to use Valiant's original example for this because I thought it was very nice. So suppose you have like a very long computation that you want to do over multiple generations. So for example, you want to prove Riemann hypothesis, but then you first prove Fermat's little theorem, and then there are more proofs, more proofs, more proofs. And finally, after many, many years, you have a proof of Riemann hypothesis. But how can you trust that every intermediate jump was a valid proof? Maybe there's a bug in the middle proof. So how do I make sure that this entire chain of proofs was actually correct? So this is the motivation for incrementally verifiable computation. So in incrementally verifiable computation, you receive a configuration CFI. There's a machine that possibly takes some non-deterministic input WI plus 1 to produce a new configuration and so on. You can keep going. So the point is there's like an incremental feature to this computation. Now, how do I make this verifiable? So to do that as standard in the SNARK setting, we'll first have a common reference string. And I'm going to define a new prove M algorithm that takes as input the configurations as well as the witness. So now, along with the configurations, I'm going to attach to it a SNARK proof pi. So the point is I can incrementally update the proof as I perform more of the computation. So the efficiency requirement here is that I want the proof size, so the pi i's, to have size and verification time independent of the total length of this computation. So if I do a computation for capital T number of steps, I want the runtime of the verification and the proof size to not grow with this parameter T. And of course, soundness, it's quite natural to state, but basically it should be very difficult for you to come up with proofs that some CF0 reaches CFT if that's actually not true. And in IVC, you standard to consider adaptive soundness. Okay, so in this work, we wouldn't consider knowledge soundness because we're focusing on standard assumptions. So we only care about soundness in this sense I've written here. So just to contrast IVC with SNARKs, you can think of an IVC as essentially like a multi-hop SNARK. So in the SNARK setting, you have all the configurations in your hand. One person batches them all together to come up with a single proof pi. In the IVC setting, you should really think of like different provers who get different proofs at each stage. So for example, the first guy gets the previous guy's proof and doesn't have to keep, but he doesn't have to pass that along to the next person. So essentially, you only need the previous configuration to be able to generate the next proof. So that's like this incrementality aspect to the proof. So this is the main difference between SNARK and IVC. So here's one application of IVC I'll state. So this is definitely cherry-picked based on one of our theorem statements. But essentially think about this scenario where there are n parties who are voting. And suppose they encrypt their votes under a re-randomizable scheme, encryption scheme. So the point is I still don't have an anonymity in this scenario. So maybe you have L intermediate authorities who go along and shuffle this, shuffle and re-randomize this list of votes. So the point is, as long as one of these intermediate authorities was honest, at the end of the day, I'll get a shuffled list of encrypted votes that maintains anonymity. But the problem is, maybe one of these authorities tampers with what's under the hood behind these proofs. So we are to ensure that this last list is in fact a shuffled list, shuffled version of the first, the actual encrypted votes. So here you can imagine using a zero knowledge IVC to make this work. So so each authority will also attach a IVC proof of each shuffling step to prove that they have in fact shuffled the original list and not tampered with the underlying votes. Okay. And I really want to emphasize here, this is really a non-deterministic computation. You really want randomness in each of these steps. So that's why the focus of today's talk is IVC for NP rather than deterministic computations. Okay, so how do we construct IVC? So I'll start off with mentioning what Valiant's recipe for IVC was in his original work that also proposed IVC. So the idea is quite simple. So suppose you have two proofs, one that proves that CF prime is reachable from CF, another that proves that CF double prime is reachable from CF prime. I want to just be able to merge these two proofs to come up with a new proof. This is a very simple idea. So the first property we would want from such a thing is to say, well, okay, if I can give you a proof for the new statement, I can in fact actually extract underlying proofs for the underlying statements. So if you have a proof of knowledge type of property from this merging step, then you're good to go for soundness. And I'll illustrate this once again. And the second property you want is succinctness. Essentially, you don't want the new proof pi double prime to be just the two underlying proofs concatenated. You really want it to grow roughly with the length of just one of the two proofs. So if you have these two properties, I claim that you have IVC. And to see that, proof merging implies IVC. I have an animation for this. So first, suppose you can come up with the proof that CF1 is reachable from CF0. Then you'll do another proof of CF1 to CF2. And now that you have two proofs, you can aggregate them to get a single proof that goes from CF0 to CF2. And then you can keep going. And now you can come up with more proofs. And now when you have two level I proofs, you can merge them again. So the point is by merging it in this way, okay, I'll just go through the animation. So by merging it this way, the point is I will only ever maintain one proof per level. And there are most log T levels for T hops of communication. So the proof size only grows logarithmically with the total number of hops. So this way I can get proofs that are independent of capital T, so only grows with log T. Okay, so this is how proof merging implies IVC. And value simplet has a very simple instantiation. You just snark the snark. So the merge step is essentially going to be a snark proof proving that you have snarks for the underlying levels and so on. So I'll call that level K proof and level K plus 1 proof. And yeah, that's it. This is very simple, very nice, and very elegant template of Valiant. And oh, I see. I made an update to this slide, but basically what I wanted to say here is that many constructions in practice actually really use this template. They use this recursive composition technique to come up with IVC constructions. But yeah. And okay, so the strategy is pretty simple. You just basically keep extracting until you get to the base layer. And at the base layer, you can tell which of the configurations are not reachable, and you'll get a contradiction. So basically, once you have extraction, the proof is simple. I will say this is an intuitive sketch missing many details. But yeah, that's the proof strategy. But the goal for this talk is IVC from standard assumptions plus IO. So the first problem here is that snarks with a K, so snargs with knowledge extractions do not exist from standard assumptions. And it seems like extraction was actually very important in the proof sketch that I showed earlier. So how can you possibly, instead hope to get IVC if you don't have snarks? But actually, we do have snarks with a K in the random oracle model. So wait, do we have IVC in the random oracle model? So can you just like instantiate Valiant's template and call it a day? But turns out no, because valiance construction, if you look at it, if you unroll it to the random oracle level, you'll first use the random oracle as an oracle, and then when you're proving the underlying statement, you're using the random oracle as a concrete function, which is part of the statement that you're proving, and then you're using it as an oracle again, so the recursion, like, keeps going back and forth. This is really bad. You cannot double dip the chip. You cannot assume your random oracle is both a oracle and a concrete function. This is Vinod's favorite Seinfeld reference. Yeah, so basically, there is a security gap. If you try to use this random oracle type, random oracle based snarks, you have a security gap. We don't know how to construct snarks in this random oracle model. And in fact, we don't think there exist snarks for these type of relativized statements. And there's this work that shows this. There are also just other barriers to IVC for NP in the random oracle model, but by this work, I forget the authors, Nielsen and I forget the other author. But yeah, so it seems like even though the snark with the K problem is completely solved in the random oracle model, IVC isn't. So it seems like, they're two different problems. So nevertheless, we're going to ask in this work, how do we construct IVC for NP from standard assumptions? So here's a TLDR slide of the two results we have in this work. So the first result, we construct IVC for NP via rate 1 bargs and snargs for NP. And turns out these things we know how to do from standard assumptions. And here we get a proof size of poly lambda, the size of one configuration, and log and polynomial in log t. And this really relies heavily on tools from prior works that construct IVC for deterministic computations. And the second, you can call it a pure IO approach, as Brent coined earlier. We construct even more succinct IVC for what I'll call trapdoor NP languages via a pure IO approach. And here we get proof size better than the first case, where we get poly in just the security parameter, independent of the intermediate configurations. I'll define this when we get to the theorem statement. And for both of these constructions, we actually achieve zero knowledge, but I will not focus on that in this talk. Okay, IVC for NP. So our first result is that there exists IVC for NP, assuming the sub-exponential hardness of non-adaptive snark for NP, and rate 1 somewhere extractable bargs. I will not define them in this talk, but I'll give intuition for what they do and what properties of them we need to get our construction. And we get a proof of size lambda in one configuration. And the point is, it's really independent of the total number of steps t, but even though it still grows with one intermediate configuration. So to achieve this result, you can think of this as incremental, if you say, from this prior work that constructs IVC for P. And the point is we show that if you carefully do some complexity leveraging, you can get IVC for all of NP. So in the prior work, it was shown that rate 1 bargs imply IVC for deterministic computations. And in this work, we show that with sub-exponential assumptions, we get IVC for all of NP. I guess another interesting thing is that this addresses this common misconception that this Gentry-Riggs barrier towards adaptive snargs rules out IVC for all of NP. But actually, we're saying, no, that's not the case. We can construct IVC for NP from standard assumptions. OK. So how do we do it? Actually, we're just going to use values recipe, but a slight twist. So before we said we wanted a proof of knowledge. Given a proof of a merged proof, I can extract both the underlying proofs. But actually, you can get away with something simpler. We can get away with what we will call somewhere extraction, which means roughly speaking, I can extract either pi or pi prime. I can extract one of the two proofs, but not both simultaneously. And turns out that's actually achievable from standard assumptions. So this is exactly what you can get out of a batch argument. But just to motivate why this doesn't run into impossibilities, roughly pi double prime is at least as long as one of the two proofs. So information theoretically, you can actually embed one of the underlying proofs inside the new proof. So you can hope to extract one of the two proofs. You just can't extract both. And to achieve the succinctness, we just need this barg to be rate 1. And there are many, many constructions from standard assumptions that achieve rate 1. So the construction is very simple. So for the base layer, whenever I'm talking about one-hop statements, I'm just going to use a snark for NP. And the point is, by using a snark for NP, you can remove the dependence on the size of any non-deterministic witness. Beyond that, oh, sorry, I'm going the wrong way. After that, I'm going to do proof merging as per usual, but this time with a rate 1 barg. So this is the whole construction. And why is somewhere soundness enough to argue this? The point is, if I have a cheating proof in the first layer, I just only need to go down one path to find one cheating hop. So I can just say, okay, I'll find one of the two sides where I'm cheating on, keep going until you get to the base case, and then you can say I've contradicted the snark security. So the same argument as before, except I'm not going to extract the whole transcript. I'm only going to extract the one hop where I'm cheating on. And the main technical thing that we do in this work is, is showing that actually by doing some very careful complexity leveraging, you can still get meaningful rate 1 length in your barg proofs that is sufficient to implement this template in the NP setting. So yes, so that's basically the result. And yay, so now we have IBC for all of NP. And one interesting thing I want to say is that actually, if you don't care about the proof size growing with a single intermediate non-deterministic witness, you can get a result that doesn't use IO, and it only uses summary extractable bargs. So in particular, that means somehow I can get IBC for NP in the standard model from assumptions from which I don't yet know snargs for NP, which I think is a very interesting thing that happens, even though in the random oracle model, things are the other way around. But yeah, so this is great. So we solved IBC for NP with this configuration size dependence. But I guess after we got this, we were not very satisfied yet, because we know adaptively sound snargs, which have polylambda proof size completely independent of statement size. And we just saw Brent's talk on this. So we were like, can we actually get polylambda size proofs also for IBC? And it seems like actually we're kind of doomed if we use this proof merging template, because we are stuck at this configuration size dependence. You sort of need to extract intermediate configurations to be able to get a contradiction at the base layer. So can we construct IBC without any extraction? And so we are trying to construct snarks without extraction, and this definitely smells like obfuscation. So that's the route we'll be taking. So our second result is we get even more succinctness, although not for all of NP. So we show that there exists IBC for what I'll call trapdoor computations, assuming sub-exponential hardness of IO and injective PRGs. So when I say a trapdoor computation, I mean that there exists an efficient way to check if a state xj is reachable from xi. So this seems like a very strong condition, but I'll try to justify it in the next slide. But basically, I can tell true statements from false statements with the help of a trapdoor. And now in this setting, we can get proof size polylambda. One thing I want to emphasize here is that the trapdoor actually is only going to appear in the proof. So in fact, you can actually hope to generate the CRS in situations where you don't have the trapdoor and yet guarantee the soundness of the scheme, assuming only that a trapdoor exists. So that's a very nice feature of this construction. And again, to show what I mean by trapdoor computations, I'll use this verifiable shuffling example again. So here, there is a very simple trapdoor. If I have the secret key for the encryption scheme, I can take any intermediate two states, decrypt it, and check the one as a permutation of the other. So there is a very simple trapdoor for this computation, but yet making these non-deterministic hops is very important for functionality in this particular verifiable shuffling example. So now one consequence of our result is that you can actually get a multi-hop verifiable shuffling scheme with very short proofs from just standard assumptions. So this was actually not known before this work. So here's a very cool interpretation of this trapdoor NP restriction. So going back, yes, the trapdoor only appears in the proof. And the techniques used here are very highly inspired by this pure IO adaptive snark construction. I don't have time to fully go over the details of this, but the basic idea is I want to do the proof without extracting anything. I'll actually state the construction because the construction is quite simple. So the verification algorithm is basically just going to take in as input x0, xi, and a signature, and checks if it's a valid signature. The proof algorithm takes as input a proof of the previous hop, as well as a new witness, uses the IVC.v algorithm to check if it's a valid witness, and if yes, puts the next signature. Basically, it's the intuitive thing you'll try to do if I'll give you black box obfuscation. You would just say sign it if you have a valid signature for the previous thing. And the CRS is just going to contain obfuscations of these two programs, and that's the whole construction. And in fact, if you have virtual black box obfuscation, you can show this is secure for all of NP, but we don't. So we use this trapdoor to help us buy something. So the high level idea is in the real world, I'll have the real scheme. Then we'll do a lot of IO gymnastics, see paper, and we'll use a lot of ideas from the previous talk. And the hope is that we get to an ideal hybrid where there are no proofs for false statements.
We just have 1 minute left.
Yeah, I'm done after this. But yeah, basically once you get to a world where there's no proofs, you can just say if you have a cheating prover, you have a distinguisher. And the existence of a trapdoor lets you basically compute the cheating prover success probability, so you can actually use a cheating prover as a distinguisher. And the point is, we did not use any extraction here. The trapdoor helps us get around this, and we just went to a world where there are no proofs instead. Okay, to summarize, to extract or not to extract, can we take this like not IVC approach without extraction further and get it for all of NP? So yeah, we showed two IVC constructions in the non-deterministic setting. The first was extraction based, and we get proofs of size that grow with one configuration. We then give an IO based approach to IVC for trapdoor NP, where we achieve poly-lambda size proofs. Can we extend this second approach to all of NP by using more ideas from the prior talk? Okay, thank you.
Hi, thank you for the talk. And I wanted to ask a simple question. When you go to the construction number 1, what's roughly the intuition why you need both of those? Because you could theoretically try to compute this tree either using those bargs or either the snarks from MP from IO.
So the barg gives you the property that you can extract one of the underlying proofs. Snargs with a G do not give you this. And we don't think snargs with a K exist. So that's why we want to use bargs when we do the proof merging. At the base layer, a snarg is good enough.
All right, thanks.
Yeah.
Have you tried building rate 1 bugs just on pure IO?
So if you use SSBs, like a rate 1 SSB plus a pure IO construction, you do get something like this. So I imagine if you can come up with like a rate 1 SSB type analog from pure IO setting, like maybe like a positional accumulator with rate 1, then maybe you can get something like this. I haven't tried.
Okay, thank you.
Okay, let's thank Surya and all the other speakers in this session.